In a quiet municipal museum in Germany, for decades it sat inside a drawer. It wasn't lost, merely unseen. A thin slab of Solnhofen limestone, world famous for preserving the delicate ghosts of Jurassic life. On its label, a simple, dismissive classification, unknown fossil. It was just one of thousands of such slabs, a piece of noise in a vast collection of data. But what does it mean to be unknown? Is a thing unknown if no one is looking? Or does it become known only in the instant it is finally understood? The slab itself held a secret coiled within the stone, a 120 million-year-old contradiction waiting for a curious eye. That eye belonged to paleontologist David Martel. He wasn't even looking for snakes. On a student trip, he was simply showing a class what Solnhofen fossils looked like. And then he saw it. An impossibly long spine, a flourish of ribs, a distinctly serpentine form. This alone was unusual, but not unheard of. But then, his gaze drifted to the sides of the elongated body, and there they were, tiny, absurd, yet perfectly formed, 4 legs. It was a moment of cognitive dissonance, like finding a sentence with a word that shouldn't exist, but somehow makes perfect sense. The unknown fossil suddenly had a very specific and very complicated identity. The creature was named Tetrapodophis emplectus, 4-footed hugging snake. It's only about 20 centimeters long, the size of a pencil. Its body plan is overwhelmingly snake, an elongated trunk with 160 vertebrae, far more than any lizard, but fewer than many modern snakes. The tail is short, and its ribs extend far down its body, all classic serpentine traits. But what about the head? Its skull is not quite the hyperkinetic apparatus of a modern viper or python. It's more robust, more lizard-like in some ways. It's a mosaic, a creature caught in the very act of becoming something else. Let's look closer at those limbs. They are not useless vestiges or tiny nubs. They are perfectly formed, albeit minuscule. The front legs are just 4.7 millimeters long. The back ones, a slightly more robust 7.2 millimeters. And on the end of each limb, something truly astounding. 5 distinct digits, a tiny hand, and a tiny foot. You have 5 digits on your hand. A lizard has 5. This is the ancestral blueprint for tetrapods, for all land vertebrates. But why would a snake need hands? These weren't for walking. The proportions are all wrong. So what were they for? The second part of its name, emplectus, means to embrace or to hug. The researchers who named it proposed these limbs had a function, not for locomotion, but for grasping. Perhaps for holding on to a partner during mating, a behavior we see in modern snakes like pythons that still retain tiny spurs, the remnants of hind legs. Or, maybe even more compellingly, they were used for gripping struggling prey. Imagine a small lizard or amphibian caught by Tetrapodophis. As the snake constricts, these 4 tiny 5-fingered hands dig in, anchoring the victim, preventing its escape. They were tools, not transportation. The existence of Tetrapodophis brings up a fascinating point about your own body and the bodies of all animals. Evolution doesn't always throw things away. Inside the DNA of a modern python, the genetic instructions for building legs are still there. Genes with names like sonic hedgehog are the master architects for limb development in vertebrates. In snakes, these genes have been mutated, or the switches that turn them on have been broken over millions of years. They are silent instructions for a body that is no longer built. Tetrapodophis is a physical snapshot from a time when those genes were not yet silent. It's a fossil not just of bone, but of a functioning genetic pathway. Where did this creature live? The fossil itself gives clues. The long body and short tail are hallmarks of a burrower. Think about modern animals that dig through soil or sand. They are often elongated, with reduced limbs to minimize drag. This morphology is seen again and again in unrelated burrowing species. The discovery of Tetrapodopus gave a huge boost to the theory that snakes evolved their legless form not in the water, but on land, as creatures that hunted and lived underground. The legs of Tetrapodopus could have acted as anchors, helping it push and maneuver through soil and debris. This fossil wasn't just a new species, it was a key piece of evidence in a century-long debate. However, science is never that simple. The story of Tetrapodopus has a twist. A few years after its celebrated announcement, another group of scientists challenged its identity. They looked at the same bones, the same slab of limestone, and came to a different conclusion. They argued that the skull, the tooth structure, and certain aspects of the spine were not like early snakes at all. Instead, they proposed it was a dolichosaur, an extinct group of long-bodied marine lizards from the Cretaceous. This doesn't make the fossil less amazing, it just shifts its position on the tree of life. Is it our snake's great-great-grandfather, or a very strange cousin? The debate continues, written in the language of tiny bones. Regardless of its final classification, the journey of this small fossil is a powerful story about observation. It rested in obscurity, classified as nothing, because the defining features that made it extraordinary are almost microscopic. It took a prepared mind, a chance encounter, and a willingness to look closer than anyone had before. How many other revolutionary discoveries are sitting right now on shelves, in drawers, or in digital archives, labeled unknown? They are hidden not by rock or time, but by our own attention. The universe is full of four-legged snakes. We just have to learn how to see them.
Monotony has grown fast. Nearly 2,700 people have watched in the last few weeks. Yet less than 0.03% are subscribed. It would mean a lot if you joined by hitting subscribe. And again, thanks for watching.